Okay, question 8, got some circuits questions. So we've got a student investigates resistors connected in parallel using a number of resistors. Each resistor has the same resistance. Here's the circuit diagram with one resistor labelled R. Add to figure 19 a voltmeter to measure the potential difference across. So we know we've got to connect that in parallel. There we go. 1 voltmeter in. And another resistor in parallel with resistor R. Okay, no problem. Job done. Just making sure that I've got it all connected and there's no gaps. Yeah, done. State the measurements that students must take to find the overall resistance. Well, we're going to need this beauty again. I'm very rich, and we know R equals V over I, so we just got to use it. So R equals V over I, so you need the potential difference drop across the resistors and the current in the circuit, because that will then enable us to calculate it. So you can see I've just used the formula, rearranged it, and then talked about I need the voltage and I need the current. Okay, student investigates how the overall resistance changes with additional resistor added in parallel. Each resistor has the same resistance, so same as before. And we can see we've got a curve. So I'm just gonna get that is awful. Let's try that again. There we go. That's not too bad. State the resistance of a single resistor. Well, there's one resistor, and I get that as 1 ohm. Comment on the relationship between the overall resistance of the circuit and the number of resistors in parallel. So as we increase the number of resistors, the overall resistance decreases. Fine, we're happy with that. So talk about X, talk about Y. And we can see it's a non-linear pattern and that it flattens out to and then it levels off. So as the number of resistance in parallel increases, the overall resistance decreases at a decreasing rate. That is, it's non-linear. And then it says use information from figure 20. So that just means pick some numbers. We need to pick some numbers. So I've just gone 2 resistors is 0.5, 4 resistance equals 0.25. So we can see that we've got a doubling the resistance and a halving of the doubling the number of resistance and a halving of the total resistance. There we go. A different circuit is then set up with 2 resistors as shown in figure 2.1. Calculate the potential difference across the 15 ohm resistors. So there's 2 ways of doing this. The easy way, which is just using I'm very rich. So we know we want V equals I times R for that one. So that's just going to be 15 times 0.2. Gives us 3 volts. There's another way of going it if you want to really make it complicated for yourselves. And we could work out the total resistance. So if total resistance is 35. And then work out what's the total voltage across both. And then we could do the complicated bit where, well, this one's going to be 15 out of a total of 35 times the total in is 3 volts. They both give the same answer, but clearly that's an easier way of doing it. Okay, next one, calculate the total power dissipated when there's a current of 0.2 amps. No problem, no unit change there, and we've got to use P equals I squared R, and it's that usual thing of students just forget to square the current. So 0.2 squared times 35, because that's the total resistance, because we want the total power, so of the 2 resistors, and we get the power equals 1.4, and that is that question done.